last unit of new material, and a lot of it you guys have seen before. You do know what a 3D figure looks like. You know what the word prism is, cone, things like that. Some of it may be new, like I'm not sure you know what a slant height, I think lateral height might be up there as well. No, it's not. Okay. Anyway, there's certain things that you may or may not know what they are. So this is kind of like a little bit of a word bank. I was kind of just glancing at it. We'll see, hopefully I got all the words that were there. But if we go ahead, polyhedron, that's a word that if you don't know, you should know what it is. But it is a 3D figure that's made up of a bunch of polygons. Okay? So all the faces are, in fact, polygons. And there's all different kinds. Prisms are polyhedrons. Pyramids are polyhedrons. I've even got one made over here. Someone actually made a polyhedron. It's just a 3D figure whose faces are all polygons. Okay? It doesn't have to be the same polygon. It can be different polygons. Okay? What about the blank is what each surface of a polygon is called? That's the face. Okay, so we know that the surface is called a face. Prisms are named for the shape of their bases. Okay, you can have hexagonal prisms. You can have triangular prisms. You can have all kinds of different shapes of prisms. But the bases are the ones that they're named for. What's a solid that has two congruent bases that are circles? Okay, so they're circles. And so a cylinder would be that. That is one. Another option would be a prism is a solid that has two congruent bases that are polygons. Either one of those would have fit there. Okay? So I'll give you choices. So this could have been a prism, and this could have been a polygon. Okay? Either one really would have fit that fine. What about number 5? The point where 3 or more faces meet. What do you think that's going to be called? Vertex. Good. Okay. Like the points of the polyhedron. All right. Number 6. A blank is one whose lateral edge. What do you think a lateral edge is? Okay. So look, can you mind holding yours up, Jonathan? The one that he made. Okay. Hold it up high. What would a lateral edge of that be? Like the actual where the two faces meet, right? There's like the kind of like the edge of that. Okay, so the lateral edges are parallel to the bases. Oh no, I'm not sorry. Hang on, not parallel. I think that should be perpendicular. Let me think about this. I get what this is trying to say. A prism. Can somebody make a prism for me real quick with your thing? Go ahead and someone make a prism. We have a polyhedron. Let's make a prism. So, y'all go ahead. I asked you to pick up a bag out of the blue box. So let's follow directions. Go ahead and grab one. Emma, since you're the closest one, would you go grab me a bag out of the blue box, please? Is this a prism? Yes, it's one kind of prism. Try to make me a prism out of what you have. Try to use different shapes for the bases. Someone make a triangular prism. Someone make a octagonal prism. Yep. Try to create a different type of prism. In order to make a prism, you have to have a bunch of rectangles and then two bases. So pick two bases, two shapes to be your bases, and then pick a bunch of rectangles to fill in the sides. So I'm going to pause this while we're making these on our own. So if you look at this particular example, I know you can't see it if you're listening to the recording, but the one that Reese has made, the green color is very clearly the bases. And what shape is that green color here? Triangle, right? All right, stop making now. Pause. Stop making. We're going to make these again, I promise. Give me a second. Let's put them down. All right, so the triangulars. This is called a triangular prism. So we call the greens the bases. What do we call, Deshay, I said stop. Go ahead and put them down. Thank you. What do we call the red faces, the red parts to this? They're called the faces. Okay, they're called the we have bases and faces, and that's hard to explain. So let's see. So if we're talking about a prism, The lateral edge is the edge where the red sides meet. What's true about it and the bases? Are they parallel or they're perpendicular? Okay, so a prism is one whose lateral edges are perpendicular to the bases. I'm not sure if that was was an option. So I'm sorry about that. Okay. All right. The height of any lateral faces of a pyramid. All right. So far we have a prism that has been created. Can somebody make me a pyramid? I'll pause. Oh, never mind. We've already got one. Already made. Okay. So we have a pyramid drawn, our pyramid. This is not the only kind of pyramid, by the way. This one happens to have a square as a base, but not all pyramids have to have a square base. So if we look at a lateral face, okay, a lateral face is made up of what shape in this particular example? Okay, so we have one base, which happens to be a square, and then we have a bunch of lateral faces. The height of a lateral face is also called the slant height. Okay, so it's called the slant height. It is the height of the triangle itself, not the height of the pyramid. They are different things. The height of the pyramid goes from the vertex perpendicular down right in the middle of this base. Can you visualize that? It's going to go right from where the vertex is straight down perpendicular. That's the height of the entire pyramid, but the slant height is the height of the actual face. Okay, a little bit different. Okay, a pyramid has what for its base? Now we thought it was a square. A square is one option, but can't we have anything as the base? Any kind of what? Any kind of polygon. So we have a polygon for a base, and often it's a regular polygon. It doesn't have to be, but in order for it not to be, we call them right, they're perpendicular. There's something called when it's slanted, there's a different kind of, but that's not in our curriculum. It has a polygon for its base, and the faces that are in a pyramid, what's always the face going to be? They're always going to be triangles. And what kind of triangles specifically? Isosceles. They are not necessarily going to be equilateral, but they will be definitely isosceles triangles. Okay, good. A blank has two congruent circle bases. A cylinder. That one's definitely the cylinder one, right? And what's true about those circles? They are parallel. I agree. Any of the bases will be parallel. They're going to be congruent. Okay. Now, can you make a cylinder with your information, your things that you have? Why? Okay, it doesn't curve around. We don't have circles, first of all. So when we get to nets, we're going to look at how do you draw a net for a cylinder, because that's a little bit harder to see because it doesn't, like you said, doesn't curve around. We don't have circles to deal with that kind of snap together like the ones we have here. All right. Parallel is true, but more specifically, you can write parallel and congruent. How's that? Because both are true. I agree. Yes, ma'am. It does actually. Oh, it does say congruent. Huh. Good point. See, India, I think you're actually right. And Amira, you're right. It says congruent here. So we're kind of repeating, right? So I think India and Amira are right. I think we should say parallel. Because it already said congruent in the problem, didn't it? Good point. They're both true. Good job. All right, what about number 10? The segment in a cylinder that is perpendicular to the base is called the height. Very good. Cylinders have heights as well. What has a vertex and a circular base? A cone. Okay, again, something that we can't create with our 3D figures. Emma, just please stop for just a second, okay? Let's make sure we get all these right. Number 12, the slant height in a cone. If I had a cone, which I don't have around the room, I'm looking. I guess this is sort of a cone, not really. Sort of. I could create a cone very easily. How could I take this and make a cone? Like you work at Cold Stone, is that what you said? Yeah, I could make a cone. Could try to make one and just cut that off, right? All right. Pretend like this is my cone, ugly cone that it is. What would the slant height be? The height is right in the middle, but this is the slant height. I'm going to try to draw it. Like, it probably might be better. So if I had a cone like this, okay, first of all, this is called the actual height. What would the slant height be? Like the slanted one. We use that abbreviation of letter L, lowercase curved L, and you need to know that because it's on your formula sheet for the SOL. I know you don't have your SOL binders, but we'll get to that. Mm-hmm. Yes. Because if you think about, can anyone see maybe a theorem that we might use eventually when we, any kind of maybe right triangle that you can maybe possibly draw, right, between a slant height and a regular height? And so we are going to look at the Pythagorean theorem again, okay, when we talk about 3D figures as well. But yeah, this picture right here is a right triangle and a cone. And so if we're given the radius of the base and the height, could we find the slant height? Of course. If we had the slant height and the radius, could we find the regular height? Yes. Okay, so we'll look at those when we get there. The slant height in a cone is the distance from the blank to the edge of the blank. So the distance from the vertex to the edge of the base. You could say circle there if you wanted to, but the circle is the base in a cone, right? And then number 13, the set of all points. What do you think of the last one? Equidistant from a point. So the set of all points in space that are equidistant from one point. So if I have my point is my fingertip, and I want to talk about all the same distances away from my finger, and I create all these points everywhere. What shape is going to be? A sphere. Okay? So it would be a sphere. So if you look at the bottom of your page, we actually have a shape. What kind of a prism? It's a triangular prism, and whenever you're talking about a prism, I want you to be very specific, and we use its base to name it. So in this case, it's not even just a triangular, it's a right triangular, isn't it? Rectangular prisms would be a box. That would be a rectangular prism. Okay? But this one, because the bases are the right triangles, we call it a right triangular prism. I often, and if you're like me, I'm going to want to highlight the bases. So if you have a highlighter, want to borrow a highlighter, any of that, feel free to do that. That highlighter's on top of my cabinet. But it's a good idea to talk about the bases when you're naming prisms and to identify them very clearly.
Can a base be anything?
A base can be anything.
So do we really need to have like two bases, or is that only thing for?
Well, there's always going to be two. I'm going to explain. We'll get to why in a minute, but I want you to highlight both of the bases when you have a prism. And that kind of goes to India's question, because the bases in this case were triangles. What were the lateral edges or the lateral faces? They were all what? What shape? They were all rectangles. What if everything's a rectangle? So it's a rectangular prism, but it's a different formula that we're going to deal with. And there's a different formula for it on your formula sheet as well. So we'll deal with that when we get to it. If you look at this particular problem, could we name a vertex? How many vertices do you see? I see 6. Let's pick one. C, A, B, I don't care. Any of the letters, right? C. Let's name an edge, specifically a lateral edge. How many points do I have to use to name it? 2. Okay, so CE is is CA an edge? It's not a lateral edge. So we need to make sure that we are clear. So if you would please make sure we're talking about a lateral edge. Okay? And a lateral edge, there's how many lateral edges do you see? 3. CE, AF, and BD. I'm going to go ahead and just use AF as one, but there are 3 of them. Why do you think I have dotted lines and non-dotted lines here in this picture? Okay, so what if it was dotted? Why is it different than if it's not dotted? Right. It's 3D, which means that it's behind. So, and we're drawing them so we can see them. You're all saying the right thing. It just dotted just means it's behind the figure. Okay. Name the bases. How would I do that? So you would say triangle, ABC, and triangle, EFD. Are those triangles congruent? Have I written them in a way that I could write a congruent statement? Why not? They didn't correspond, right? Good. So I didn't write them in a corresponding order. I wrote them in alphabetical order, but they're still congruent. Okay? Good. Go ahead and turn the next page for me, and you'll see this. I don't particularly like this picture too much. If you look at the picture, I know. Tell me why the picture probably bothers me. We just talked about it. There's no dotted lines. I don't know what's behind, what's forward. It kind of bothers me a little bit, but we at least know what the shape is. What is the shape? Triangular prism. So do me a favor, when you have your highlighter, I want you to highlight the bases again. They are, in fact, congruent. The reason I'm having you darken in or highlight the bases is because the distance between the 2 bases is something very specific on the figure. What do you think the distance between the 2 bases is called? If I look back at the prism that Reese created, the distance between the 2 green bases is going to be called the what? The height of the entire thing. So the distance between the top and the bottom, the way I have it oriented, or if I changed it the left and the right, the distance between them is the height of the entire figure. No matter whether it's lying down on its side or upright, it's still considered its height. Okay? So how can we do that here? So this figure here is the distance between the 2 bases. So we're going to call that the height. And I'm even going to write distance between the 2 bases. Okay. What do you think about the other 2 things? What are they called? The bottom one's a base. What about the top one? What is it pointing to?
It's pointing on the edge.
It's pointing on an edge rather than on the edge. It's not really a lateral edge, but it's an edge of the base, right? A lateral edge would be this guy right here. Would you agree? It's an edge of the face. It's an edge of the lateral faces. So the slant height's something different. Slant height we really deal with when we talk about pyramids, okay? Not necessarily with prisms. I think they meant it to just be a base as well, okay? They just didn't draw it into the base itself. This edge really doesn't have anything, there's no special name for it, okay? The edge of this green, the green edges, there's no special name for that. It's just the edge of the prism? I don't know. But these red edges are the lateral edges, okay? Yes?
So then the lateral edge will always equal the height?
Yes, yes. Okay, so we're just going to call them they're both bases. Okay? All right. We keep going. The middle figure, I tried to draw mine as 3D-ish as possible. Let's go ahead and name what we know. Let's start with the top right. The top right. What is that called? Nope, the slant height is this one down here. It's the height of the actual triangle. Okay, so that's the slant height. What about the top one? What's DC? It's a lateral edge. Okay. How about A? Or this, I'm sorry, D. I'm not even sure what that is. How about this one at the top left? I don't think it has a letter at the bottom. It's just a regular old height. It goes right from the vertex, that D, straight down perpendicular to the base. And then what's the bottom? It's called a base. Okay, good. So what's the vertex in the figure? D. How many edges do we have? I counted 3. Let's name one. DA, DB, and DC. Doesn't matter which one we pick. Let's be patriotic. Okay, DC it is. Name the segment that is the slant height that's listed. I'm not sure it has a letter down here. Do you? Does it have one? Let's create one. I'm going to use K because my name begins with a K. Okay? No. 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 It is Kristen. So DK would be the slant height. It's on like Donkey Kong, right? All right, so what is this figure? Be more specific. Triangular pyramid. If they are all equilateral triangles, it's something specific. It's called some kind of hedron. We'll talk about that later. But we don't know if these are equilateral triangles or not. So we just know it's a triangular pyramid. That's all we know. Okay? There's all different kinds of special hedrons, like icosahedron, and all different kinds of hedrons that use equilateral triangles to create 3D shapes. All right, last one here. What is this shape called? Just a plain old cone. Okay? Sometimes they call it a right circular cone. Why would you think it would be called a right circular cone? What's a right angle? The height is perpendicular, okay? So sometimes you will see it written that way. When they are slanted, sometimes you'll see a cone that looks like this. And that's called an oblique cone. The one I just made, the slanted one, is called oblique. Okay? It's not in our curriculum, so we're not going to study them. Okay? Maybe we'll look at them. Okay? But we're going to be sticking with the right circular cones. But if it's slanted off to that, it's called oblique, in case you need to know. What's the vertex of a cone? A in this case. Altitude. That's another name for height. So what would it be here? AB. Good. And then we know what the figure is called. This is called the height. Ooh, what's this one called? Slant height. Good. Excellent. And what letter do we use for slant height? Lowercase, cursive, or script L. Okay? Good. Okay. So if you would, go ahead. We're going to talk about nets today. And we're going to, I have these, you have these snap cubes that are with you at your table. We're going to be using them, so you will need to take apart whatever you've gone ahead and built. But I would like us to use these to kind of decide for ourselves what the nets are. If you look at problem numbers 2, 3, and 4, do you see how it says find the surface area? Cross that out. We're not doing surface area until later. We're only dealing with nets today, basically going from 3 dimensions to 2 dimensions. So these little snap things that we have, if I was to create from this pyramid and I wanted to create a net, all you would have to do, so watch me folks before you start, without breaking it too much, of course I did. The net would simply be this for a pyramid, okay? When you're drawing a net, you're going to make sure you've included all of the faces, and then you're going to imagine them folding up to create your 3D figure. So that's why I have these here for us today, so we can kind of decide, like when you're matching 5, 6, 7, and 8, you can kind of skip 2, 3, and 4 for right now. We'll come back to those, okay? But when you're matching them up, see if you can't decide what the net's going to be. But option A, B, C, and D, we're going to deal with those quite a bit in a few minutes, okay? So go ahead and work with these. Go ahead and build your square pyramids. Decide what the net's going to look like. Is the net possible even? So we're going to come back to number 1, okay? We're going to come back to it because if you look at the next page, if you look at the very back, you have to find out all of these that make a cube, okay? So you're going to spend some time with this. Please stop building just for a minute, just for a minute, just for a minute. Thank you. So we're going to be figuring out which out of all of these make a cube. So you're going to figure that out today, okay? So we'll come back to this problem. I'll give you a hint. Only one of these does not make a cube, okay? So only one does not. All of the others do. Shh. I really don't want to take the snap things away, so please stop while we're going over it, okay? All right. So only one does not. Let's make sure we're skipping that one. Let's look at 5. What is the net that matches with 5? C, good. How about 6? D as in dog, good. How about 7? B as in bulldog. And number 8? A, good. I agree with you. Let's jump to number 9. Oops, hang on. Number 9, there we go. Which ones will make a pyramid? I'll give you a hint. 2 work. Exactly 2 will work. Any ideas which ones will work?
B and C.
B and C, good. B and C are the only ones that will work. We're going to spend the last part of class dealing with the very back page. So you're going to need to work together as a team because I don't think that you have enough of the squares to be able to figure out which ones make a cube. Shh, please listen. I'm going to tell you how many of these nets will work so you have a process of elimination and you know. But there are 11. Okay? We're going to skip that one because that one's kind of like on the back. But I'll tell you which one doesn't work eventually. So try to figure out which 11 of these work. Okay? So I'm going to pause the recording while y'all figure it out. All right, so it looks like we're about ready to go over our answers. Let's see how well we do. Which ones, so if you don't mind, just stop. I'll let you guys clean up in just a second, but just kind of stop with the building for a moment. On the first row, which ones work? First one? Third? Fourth? Good. All right, how about the second row? Only the second one. How about the third row? First, second, third? Oh, just first and third. Okay, how about the last row? First and second and third. And the last row? First and last only. So Eric, in his speediness, so impressed. Can you explain to us what you did to quickly be able to pick them out? Because I've never seen someone do it so fast. I'm so impressed. What'd you do? Did you find that when you were playing with these snap, I'm not even sure what these things are called, snap things, okay? Did you find that the ones that didn't work, they overlapped and there was like a hole in the cube, right? And so he has the ability to figure out which two are going to overlap just by looking at it, which I thought was a pretty cool thing, okay? This one, by the way, there's no overlap. What's the problem with it? It won't even fold. Would you agree? It won't even fold up, so that's an issue. But here, well, let's start at the beginning. The beginning ones are a little easier to see. If you look here why these won't work, aren't these guys going to overlap? Okay? If you look at the second row, which ones are going to overlap? These guys? Okay? So you can kind of visualize, now he has that uncanny ability to be able to do that. And that's pretty impressive, but that's what you're looking for. What are some other patterns you see? So obviously you want to pick to see if some overlap. Which ones will work? What's true about all of the ones that will work? Oh, did I pick the wrong one? Oh, I'm sorry. Those are the ones that overlap. Thank you. See, I can't even do it. So the ones that do work, the ones I've highlighted in yellow, what's true about all of them? I know they make a cube. They fold up. If you're Eric, we can visualize them being a cube, but I'm not that good. Did anyone see any commonalities between the ones that do work? So honestly, that's how I did it. I said, okay, I found one that worked, and if I just moved one of the cubes around, like one of the squares around to fit, would it work? If I moved one, the other one would have to go. If I moved this one down, this one would have to go up, that kind of thing, and it would work. I did that. I don't know what you guys did, but besides actually folding them and making them work, I guess. But I loved what Eric decided to do in terms of finding the ones that would actually overlap. That was good. If you look at your page for homework, okay, it's going to be very quick and very easy. You're welcome. It's a quick, easy assignment. If you look at problems 1 and 2, it's a separate sheet of paper, okay? You guys looking? You're going to have to write down using letters on problems 1 and 2 what letters the corners would be. Some will repeat. Why would you repeat the letters? Right. So if I take this right here, look at my, whatever this is. What is this called, by the way? Rectangular prism, where these are the bases. Would you agree? Okay. So this corner right here, if I was to fold it out and lie it flat, doesn't it touch 3 different sides? So it's going to be written out how many different times? 3. So that's what I mean, is that you're going to reuse some of these letters more than once. Okay? So what I want you to do is that's what you do for problems 1 and 2. On problems 3, 4, 5, 6, and 7, you have to add something else. I want you to, in addition to the directions that are there, I want you to also draw a net for each. So on problems 3 through 7, in addition to what it says to do, again, identify the number of polygons that are in the faces. Okay, not the bases, but the faces. I also want you to draw a net. Okay, and that's all your homework. That's it. If you would kindly put all the snap pieces back into their respective bags, you can put them back in the blue bin in the back corner for me, and we're done for today.